Hello everyone. Today we're going to talk about dimensionality reduction using principal component analysis, or PCA. The goals are to motivate dimensionality reduction to start with, then to prove that PCA achieves optimal linear dimensionality reduction, and then to show you an application to face recognition. All right, so let's get started. The prerequisites here are mostly linear algebra, so it would be good if you're comfortable with orthonormal bases, subspaces, and projections. And I have another video showing why principal component analysis can be performed by computing an eigendecomposition of a covariance matrix. So that would probably also be useful to take a look at. Okay, so what's the motivation here? We often, in modern days, we often have data sets that have a lot of features. And if you have a large number of features, it can be difficult to analyze these data sets, realize what's important, what's not important. Even processing them can be very costly computationally. So it's of great interest to find ways of reducing the dimensionality of these data sets while preserving the information in them. And as we will see, PCA is a very useful way to do this. As an example, when you're dealing with images, images are super high dimensional. What do we mean by that? When you think about it, what is an image? An image is a list of values of intensities at different pixels. And the normal image is going to have, 200 by 200 pixels, usually more if you want a high resolution image, so maybe even 1000 by 1000. The dimensionality of these data points, which is equal to the number of pixels, is equal to 10,000. If it's 1000 by 1000, it's a million, right? So it's really very, very high dimensionality. So it's it's of fundamental interest how to project these data points onto a lower dimension in order to process them, reason about them, or find interesting stuff about them. Okay, and that's what dimensionality reduction tries to do. We're going to look at linear dimensionality reduction, and in order to do linear dimensionality reduction, it's super useful to use orthonormal. This was amazing. It's super useful to use. Sorry about that, but let's keep going. It's very useful to apply orthonormal bases. The idea is the following. We're going to model data as samples from a d-dimensional random vector x. All right? X is going to have zero mean. If it doesn't have zero mean, you can always center it by subtracting its mean, which is anyways what you usually do when you're processing data. Okay, the first thing you do is you just center the data if you're going to do dimensionality reduction. And we'll see examples later. But now let's assume that X has zero mean so that we can simplify the exposition a little bit. So now for any orthonormal basis V1 to Vd, we're in d dimensions. We can express the vector, this is just standard linear algebra, as coefficients that are equal to the inner product of the vector with each of the basis vectors. This only works for orthonormal bases, of course, and then multiplying by the vector. Okay, this is just a standard decomposition of a vector in an orthonormal basis. Great. Now imagine that you want to do dimensionality reduction, which means that you want to represent the vector, instead of with d numbers, you want to represent it with k numbers. Well, something that you can do is you can say, well, I have d components. Okay, like these d components are given by the vector in the orthonormal basis, and then by the corresponding coefficient. How about I truncate this? Okay, I'm truncating it so that I only use k components, where k, I should have used consistent colors here maybe, but whatever. Okay, we're only going to use k components instead of d components. This is an approximation in the d-dimensional space, so it doesn't help us very much. We still have a d-dimensional object, but now what we can do is we can use these coefficients, and there's only k of them, to represent the vector. Okay, so now we have a k-dimensional representation where we take inner product with k orthonormal vectors and we say, look, this is the new representation of my data points, or of the random vector. Remember that we're representing the data points as samples from a random vector. this is something that I don't say enough, and I should say more. I'm just assuming that you're familiar with it, but I will say it. Each time I'm referring to a random quantity, I have like this squiggly line on top so that we keep track of what is random and what is not random. Sorry that I don't say that enough in other videos. Okay, so the key challenge, of course, is how do I choose? I get a data set. How do I choose these k vectors? This seems pretty crucial, right? Because I'm going to take inner products with just those vectors and throw everything else away. So they better be chosen well. And as we will see, PCA gives you a way to choose them very, very well. There are many possible criteria that you could think of when you're doing dimensionality reduction. At the end of the day, what you want is to preserve information. This is very difficult to capture. Perhaps naive way, but still useful way of capturing how much information you're losing is saying, okay, I have this approximation, okay, which is taking these coefficients that I'm using to represent the vector, multiplying them again by the orthonormal vector in that basis, and reconstructing the original object, the original vector x. I can see how good that approximation is. If that approximation is good, then hopefully the coefficients are preserving important information. And by good here, we're going to use the L2 norm. I do want to say that this is not perfect. And in fact, when you do this with images, you tend to focus on low resolution details that have much more energy, much more L2 norm than fine details. But it's actually very difficult to develop metrics that focus on exactly the informative feature that you're interested in. And this is a very reasonable general purpose decision. Okay, you say, okay, I want to do dimensionality reduction and preserve the L2 norm of my random vector as much as possible. Okay, so let's take a look at what we're saying here. What we're saying is, if I expanded the vector using the D vectors of this orthonormal basis, I would have a perfect approximation. But I'm not doing that, right? What I'm doing is I'm truncating and using just k of them. So I have an error. What is that error equal to? Well, that error is equal to the remaining terms, right? So here I'm truncating at k, so the error is going to be equal to what is left. The components from k plus 1 to d, which I'm essentially throwing to the trash. So how much information do those guys have? And by information, we mean the L2 norm approximation to the original random vector. Well, if you look at the L2 norm, the squared of a vector expressed in a certain orthonormal basis, what you can do is just that is going to be equal to the sum of the squared coefficients. Okay, this is true for any orthonormal basis. You can check that easily. So we're wondering how much energy is left in these coefficients, and then we realize that we can express this as the sum of the squares of all the coefficients minus the sum of the squares of the coefficients that we're using to represent the vector. Okay, this is exactly the same as this. In a way, we're kind of restating this, right? Like this is the information that is in the whole signal, in the whole random vector that we're interested in, and this is what we're preserving by just keeping the coefficients. Okay, but formally, we have expressed the L2 norm approximation error as this, which is just equal to the norm of the random vector, which we cannot really do anything about, minus the sum of the squares of the inner products of each of the vectors in the orthonormal basis, the k first vectors that we're using to compute the dimensionality reduction, that we're using to perform dimensionality reduction, the sum of the inner products of those k vectors with the random vector. This is what this term is equal to. So if we want to, and now I feel that I scribbled a bit too much on this, if you want to minimize the error, what do we need to maximize? We need to maximize this. It makes a lot of sense, right? We need to maximize how much energy, if you want. I'm using energy for L2 norm because it just feels more intuitive. how much energy the inner products are capturing. In particular, we're going to look at the mean energy or the mean inner product. So we want to minimize the error. That is going to be equal to maximizing this sum of expected values of the squared inner products. If you've taken a look at the video on PCA, like the spectral theorem, the mathematics behind PCA or something like that, is what I've called it, then you might remember that this is just the directional variance. You don't even need to look at that video, right? What is this saying? This is saying I have this centered vector inner product with a certain vector vi. That's the component in the direction of vi. What's the expected value of that square? If things are centered, it's just the variance. So essentially what we're saying here is that we want to maximize the variance captured by the inner products with these vectors. And then now, actually, probably now is when it would be more useful for you to have seen the other video. This is actually what PCA does. Okay, we want to maximize directional variance. And if you remember, if you have a random vector with a certain covariance matrix, sigma x, the eigenvectors of the covariance matrix give you the directions in which this variance is maximized. In particular, the eigenvector corresponding to the largest eigenvalue is going to give you the direction of maximal variance. If you are orthogonal to that direction, then the second eigenvector is going to give you the direction of maximal variance, and so on and so forth. Importantly, this does not give us exactly what we want because we're not ensured that the sum of the variances is maximum. Okay, we're going to prove that actually it is. Spoiler alert, in a moment, but this doesn't immediately imply it. Okay, so remember that what we want is, we want to minimize this whole thing, for which, as we're going to see in a moment, we have to maximize the sum of the variances. But, we almost have it here. This is telling us that if you want the direction of maximal variance, take the first eigenvector of the covariance matrix. Okay, that's what PCA says. If you want the direction of maximum variance that is orthogonal to that one, take the second one, and so on and so forth. So it feels like this should be it. And in fact, we're going to show that it is. I just wanted to point out that it's not completely trivial, as we'll see in a moment. The implication is not completely trivial. Okay, so it turns out that the optimal choice for these k vectors that we're taking inner products with to preserve the L2 norm, the mean L2 norm, indeed is the eigenvectors of the covariance matrix, and hence the approximation that we're actually computing is those first k eigenvectors of the covariance matrix, which are the principal directions, this is how they're called in principal component analysis, multiplied by a coefficient, which is the inner product of the principal direction with the random vector, and this was usually called the principal component. The first principal component, second principal component, and so on and so forth. What we're actually going to use to represent the data are the principal components. Okay, so the k first principal components is what you would use, and we'll see examples a little bit later. Actually, I think we're going to see an example pretty soon. Sometimes I forget what I put on the slides. In fact, we're going to see an example right now, so let's go for it. Here I'm going to show you the dimensionality reduction of a data set, which you might have seen before. It's a very famous data set, where you have 3 varieties of wheat seeds, and they have 7 features, which is the area of the seed, the perimeter, the compactness, the length of the kernel, and so on and so forth. And we want to visualize them. And in fact, we're going to visualize them and maybe do some clustering, okay? And we're going to do that in 2 dimensions. This is our goal. So what we do, we apply PCA, and we project onto the 2 first principal directions to compute the first and the second principal component. And now we can plot a scatter plot, where, for example, for this point here, the corresponding principal component, which is just the inner product between that 7-dimensional vector and the first principal direction, is equal to this, and the inner product with the second principal direction is equal to that. You do that for all the data points, and what you see is that actually this preserves interesting information for sure, because we see that the different varieties of wheat are clustered together in this low dimensional space. So this kind of indicates, in this case, that PCA is doing a reasonable job at preserving structure when we do this dimensionality reduction to just 2 dimensions. What happens if we project on the 2 last principal, if we just plot the 2 last principal components instead of the 2 first ones? I want you to think about what you expect to see here. This is what we see. Okay, so almost no variance. These are the directions of least variance in the data. Okay, not super useful, or the points are on top of each other. Okay, so then let's go back to this issue where we want to show that the principal directions, the first k principal directions, are optimal in the sense that they achieve the best possible approximation in terms of mean squared L2 norm error. Okay, so we already showed that this error is just equal to the expected value of the norm of the random vector, which we cannot change by choosing the vector, that is what it is, minus the sum of the variances. So we want to show that the principal directions maximize this sum of variances. And we almost have something like this from the spectral theorem, which we proved in another video. So my neighbor, who is quite old, is yelling in the background. I don't know if you can hear her. But yeah, there's nothing I can do about that. So sorry about that. We're going to prove that they are optimal by induction on K. Okay, if you don't remember induction, let's review it very briefly. First, we're going to say is like, what if K is equal to 1? We're just going to project onto a single vector. In that case, by the spectral theorem, we know that the best vector is the eigenvector corresponding to the largest eigenvalue. Okay, the spectral theorem completely gives us that. Now, to prove that this sum of variances is maximized by the first k principal directions, what we're going to prove is that if this is true for the k minus 1 first principal directions, then it is also true for the k first principal directions. And because we have proved it also for 1, if we prove this, then 1 will imply 2, 2 will imply 3, 3 will imply 4, and we will have proved this for any k. And that's essentially induction, okay, in case you didn't remember. So all we need to do is show that if the sum of the variances is maximized for the first k minus 1 principal directions, it's also maximized for the k first principal directions. Okay, so let's get to it. It's going to be easier to think about the expected value of the square of these inner products between vi and x. And by linearity of expectation, we can just put the sum inside here. And this is, here we're doing exactly the opposite to what we did at the beginning to justify why we're looking at variances. What is this? This is just the L2 norm of this vector that we obtain by projecting the random vector x on these k directions, right? And we can express this like this, where this fancy notation here just means that we're projecting x onto the span of vi and vk. What is the span of v1 to vk? That's the subspace of all the points that can be obtained as a linear combination of v1 to vk. And now what we realize, and this is a key insight, so if you're, if this is not very clear, you might want to review subspaces, a little bit of linear algebra. What's key here is that it doesn't matter what orthonormal basis we use of this subspace, as long as it's an orthonormal basis of this subspace. So let b1 to bk be any orthonormal basis for this subspace that has dimension k, right? Because it's the span of v1 to bk. And again, span just means every point in that subspace is a linear combination of v1 to vk. I should have used v and b, given that I'm Spanish and I cannot really make the difference very well, but hopefully it will be clear. So we're interested in this guy. This guy is exactly equal to this because we have chosen bi to bk to span the same subspace. Why all of this? Because what we're going to do is we're going to choose these guys very wisely to prove the result that we need. Okay? So this subspace has dimension k. Why? Because it's linear. Every point inside that subspace is a linear combination of v1 to vk. So there is at least one vector that is orthogonal to the first k-1 principal directions. And here you have to remember what we're proving. We are assuming that these first principal directions are optimal in the sense that maximize the sum of the variances. We need to show that if that is the case, then the k first principal directions are optimal. Okay? So, again, this subspace that we're interested in contains at least one vector that is orthogonal to these k-1 vectors. Why? Because it's a subspace of dimension k. So what are we going to do? First, we're going to show that the variance in that particular direction has to be... Actually, I should ask you, sorry. Okay, so we have the kth principal direction. Okay, I should do this more in a Socratic kind of... I should ask you and then you should think about it. I think this will be more useful. So we have this vector that is orthogonal to u1 to uk-1. Can the variance in that direction be larger than the variance in the direction of the kth principal direction? If you remember the spectral theorem, it cannot. Okay, by the spectral theorem, this variance is oops, that was unfortunate. This variance is maximized at uk for directions that are orthogonal to the first k-1 principal directions. That's what the spectral theorem tells you. Okay, so this is going to be super useful. The variance in the direction of this vector that is inside in our subspace of interest cannot be larger than the variance in the direction of uk. So now we're going to build the basis for this subspace by first choosing this orthogonal vector and then completing the basis so that it actually spans V. And you can do this with Gram-Schmidt. You can just find k other vectors that complete so that together you get the same span as V1 to Vk. And now what happens? Well, we already saw that the variance in the direction of the kth principal direction is greater or equal to the variance in the direction of this vector here. And now we can use the assumption that we've made in the induction step, because we are assuming that these guys maximize the variance for any k-1 dimensional subspace, right? So in particular, the variance that they capture is greater than these other guys that we have used to fill in the directions. So if we sum, now we have shown that by the induction hypothesis and the spectral theorem, the variance in the direction of the first k principal directions is greater than the variance in the direction of these other k vectors that span our subspace of interest. Remember that we started with arbitrary orthonormal vector v1 to vk. Then we said, okay, for that subspace spanned by them, we can choose whatever we want, and then we chose very wisely. We chose this guy that was for sure orthogonal to the first k-1 principal direction, so that we got this. And then by the induction hypothesis, we had this. So summing up together, we have that the sum of the variances in the direction of the k first principal directions indeed must be greater or equal to the sum of the variances in these other arbitrary k directions. I will listen to the recording after this because my neighbor continues yelling here. This is the problem with living in New York City. I hope it was definitely distracting me. I hope it didn't distract you guys too much. But, that completes the proof. We have proved that PCA is optimal in that way. Okay, so now let's take a look at an example. We have a data set of 64 times 64 images from 40 subjects. There's 10 images per subject. The vectorized images have dimension 4096. Okay, that's 64 times 64 if I hadn't made a mistake. And here you can see some example images. So now the PCA, first, as I said before, we were assuming that our random vector was centered. When you have a data set, usually you center it, and this is the mean phase that you obtain by computing the mean. This is just the pixel-wise mean of all the images. Then you compute your covariance matrix, your sample covariance matrix. You compute the eigenvectors that give you the principal directions, and those are going to have the same dimensionality as the images, so you can put them into an image. And this is what you see. This is the direction of maximal variance. If you're orthogonal to that guy, direction of the second direction of maximal variance, orthogonal to that, you get this, and so on and so forth. In general, what we observe here, which is super common when you work with images, is that the first principal directions capture coarse level details. You see here the eyebrows, the glasses, because we have a phase data set, right? And those are in every image. So you have a lot of variance along those directions. As you go to higher and higher principal directions, you start seeing more fine scale details, okay? Until you get very, very fine scale details here. So there's less, so what I want to point out is there's less variance in these directions, but still there's important information here. So you are losing something where you're just using a general purpose method such as PCA, because you might actually be very interested in some of these fine scale details, okay? There's always a, there's always a trade-off in life. So let's remind ourselves of the approximation that we're making. What we're saying is we have the mean, because things are centered, plus a certain number of principal components times the corresponding principal direction, and the principal components are just obtained by taking the inner product with these principal directions that I just showed you, which are eigenvectors of the covariance matrix of the data. Let's take a look at the picture. This is the mean, and now we always have the same basis vectors, and they are multiplied by the corresponding principal components. And these 7 numbers are the ones that we would actually use to represent this particular phase. Okay? We can also project back to the phase space by actually computing this approximation, and this is how we're approximating this guy's phase. As you use more and more principal components, the approximation is better. So here, this was the original. This is what happens if you approximate this poor guy with 5 principal directions. 10, 20, 30, 50. Eventually, the approximation actually becomes pretty good until it's perfect when you use all the dimensions. The data are centered. This is why this is equal to, this is, in case you're wondering why this is 359 and not 360. The last one is meaningless because they're all linearly dependent because the data are centered. That's not super important. Here you can see this effect that I was pointing out before, where for the dimensionality reduction with a small number of principal directions, you're mostly using features that are coarse, that are quite low frequency. And this is very common when you do PCA on images. Okay, so I do want to emphasize that what you would be using when you're actually processing the data based on the principal components is not obviously this image, because this image still has the same number of pixels, right? What you would be using is these coefficients. Oh wow, now I have to go back, but I'm committed, I will do it. You're using these coefficients. Okay, these are the coefficients that you're using to represent the image in the low dimension. To show you an example of that, we're going to see an application of a very simple machine learning algorithm to perform face recognition on this data set. Okay, so I have a training set with 360 images, and then I'm going to have a test set with 40 images. And we're going to identify people just by comparing the test image to the training set. Okay, so we could do this just directly with images, pixel by pixel. We take the new image and we compare it to the training set, and we choose the image that is closer. I have to tell you that this is a super bad idea in general for images, because if someone changes pose just a little bit, or like this or like that, then this distance is going to be huge. Okay, this is why images are difficult, right? You have to understand that there's an object within the image and so on, and in particular, convolutional neural networks are really good at this if you train them with a lot of data. But here we have this simplified data set where people pose is more or less the same, right? Like the nose is covers more or less the same position in terms of pixels and so on. So this is not completely crazy for this particular data set. But I did want to warn you about that. Okay, so that's a reasonable way to do this. We classify a new point, and the issue here is that this is quite costly. Okay, you have to compare all the pixels with all the pixels with the whole data set. So you have n points in your data set, it's n times the number of pixels. This is quite computationally costly. And you could have higher resolution images. This, of course, with modern computers, this is not that much of an issue, but still. So we would like to do dimensionality reduction. What are we going to do? We're going to take the covariance matrix, find the principal directions, find the principal components corresponding to each of the faces, and just choose k of them, the k first ones, because they capture the most variance. This is what I'm showing you here. We do that for every training point, and we also do that for the test image. Importantly, for the test image, we project onto the principal directions from the training set, right? We're not doing PCA also together with the test images. Okay, the test image, we just use it to identify the faces. But in order to be able to operate in this low dimensional space, we have to project it using the same principal directions that we have computed from the training set. Okay, so we do that, and now we compare and we see what is the closest face in terms of these k principal components. And now the cost is much less, right? Because I'm only comparing k principal components instead of d pixels. But there's a catch here, which is that computing the eigen decomposition is actually very costly. But you only have to do it once. What people in practice do is there are ways of making this eigen decomposition less costly when you only want the k first principal components. And a popular technique for that is randomized principal component analysis. I recommend that you check it out. Anyways, what happens when I do it on this example? Well, what I see is that this is the errors that we make over the whole test set of 40 images. If you use all of the pixels, you have an error of 4. So you make a mistake for 4 people and you get the other 36 right. And this is the number of principal components used. And what we see is that we achieve at an error of 4, which is what we achieve with all of the pixels, already by just using 40 numbers instead of 360. And even with 15, you already get a pretty good error. You get 5, only 5 wrong. So this is just 15 numbers. So it's pretty cool. Like for this data set, this actually works very well. In fact, for other data sets, you could think that in some cases it might actually help to eliminate some of the higher principal components because you're eliminating possibly features that are noisy and might not allow you to identify well. Okay, so it's not obvious that this is always going to be decreasing. Again, principal component analysis is optimal for L2 normal error approximation. It's not necessarily optimal for example, for face recognition, because you are throwing, on the one hand, it's true that you're throwing away principal directions that do not contain out of energy, so maybe they contain noise, but you're also throwing away features that could be very useful to identify. Okay, so there's the two arguments to be made. Let's take a look at what we're actually doing. So we have this test image. We're going to use 41 principal components to represent it. We can actually see the approximation corresponding to those 41 principal components by just multiplying them by the principal directions and summing them to the mean. And if we do that, this is what we have. So here we see kind of what we're preserving. Because the first principal directions have glasses involved, we see that we are kind of putting glasses on this poor guy. And on her also a little bit, and on this guy. This is just because apparently, glasses capture a lot of variance in this data set. So when we project on the first 41 principal components, you have this artifact that appears. Okay, so then what do? You compare these 41 numbers to the 41 numbers corresponding to each image in the training set, and the closest one happens to be this one in this case. Again, we're projecting these 41 numbers from the closest image back to image space so we can visualize it. And this is how they look. again, there's these spurious glasses that appear. And in this case, the glasses are kind of a problem because with these spurious glasses that appear, the closest image we will see does not correspond. Like here we make a mistake. But for the other two, okay, we're actually doing pretty well. So now let's look at the actual image in the training set that corresponds to these approximations, these low dimensionality approximations, and it's this one. Okay, so here we got it right, we identified the right person, here we identified the right person, here we did not. So this is one of the 4 mistakes that we make in the dataset. Okay, so that's all I had. We have learned that PCA achieves linear as optimal, an optimal approximation in terms of L2 norm error. This is mean L2 norm error. So in particular, for example, this is not necessarily optimal for face recognition, but still it's a general purpose method for a dimensionality reduction for which we can prove that it's optimal in a certain sense in terms of mean L2 norm error, and it's super useful in general. Thank you very much.